So I will talk about events, subsystems, and quantum reference frames. This is based on work together with Flaminia, Alessio Belenkia, Czaslaw, and Ognian Oreshkov. So we already heard a little bit about quantum reference frames in Flaminia's talk, in particular how quantum reference frames can be useful to understand better situations in which the background spacetime is not fixed by jumping into the proper quantum reference frame. So in this talk, what I would like to do is to flesh out this a little bit more, and in particular to question what would happen to the notion of event in such situations. My talk will be divided into 3 parts. So in the first part, I will introduce a quantum clock as a system in a superposition of energies that in the limit of very high accuracy gives rise to such a situation where the spacetime background is not necessarily fixed. This is just to introduce the problem, and then I will introduce clocks as reference frames for time. And I will jump from the description of dynamics from one clock to the description of dynamics with respect to another clock, to analyze what happens to the temporal localizability of events. We will see that if an event is well localized with respect to Alice, let's say, as a point in time, in space-time, it is not necessarily so with respect to Bob. So it's there is a relativity with respect to whether an event is localized or not, very much alike the relativity of entanglement in quantum reference frames. And then I will talk about the nature of subsystems in quantum reference frames, because I think thinking about subsystems is the key to understanding these effects. So I will start very basic. This is a picture you have all seen as a quantum circuit. The boxes represent things that happen to a quantum systems, POVMs, unitaries, etc. And the wires represent quantum systems that come in and out. And we have the machinery to describe what happens in each of these boxes. But of course, we need some extra input to, say, compute the probability of the whole sequence of events in the circuit that is not given to us a priori by the, say, Hilbert space formulation of quantum mechanics, because this doesn't tell us what is the order in which the boxes come, of course. What tells us in the order in which the boxes come is space-time, of course. So these events are now depicted here as points in space-time, and we have light cones emanating from each of the events. So for example, the fact that B is outside the light cone of A tells us that we should compose these operations in parallel. On the other hand, D is in the future light cone of C, and therefore we compose this in sequence. So this is kind of the basic picture, and the interesting question, at least in some toy models that I would like to present, is what happens when this structure is not there, or mildly not there, like in a superposition, say, of being in one way classically and in another way classically as well. So what do I mean by this red stars, the events? I would like to define the events not necessarily mathematically, but operationally, like something that happens to a quantum system. What I will, the model of events that I will talk about in this presentation is some measurement, some unitary that is applied to a system of interest. In this case, the system of interest is this blue ball that, for example, if it undergoes a measurement, I will model it as an interaction between the blue ball and this red ball that records some information about the interesting quantity of the blue ball. And I will label the events by clocks in the vicinity where the event happens. Then I will talk about the event as the thing that happens to the system when the clock's hand is at, say, 12 o'clock. And then I will say that the event of Alice is earlier if the hand of the clock shows a later time than the event of D, for example. And this will all be, of course, with respect to a given trajectory of the clock in space-time. So this is the general kind of conceptual picture that I will try to, investigate in this talk. And I will focus first on one of the elements of this definition, which is the clock. So what is a clock? I think this is a difficult question in general to answer. There's many features we would like for a system to fulfill in order to be called a clock. But there's one condition that is, I would say, a necessary condition, not necessarily sufficient. But a clock should be some system that is in a superposition of energies, because otherwise it doesn't move and you cannot use it to measure time, right? So within this condition, the easiest thing that one can think of is just a simple qubit in a superposition of two energy eigenstates, E0 and E1. And the way we would use this thing as a clock is we would prepare it in a superposition of equal weight, say E0 plus E1, and then we would wait until this plus here, becomes a minus. Then it becomes an orthogonal state, and we are certain that the initial state has changed, is completely different from the first one, perfectly distinguishable, and then we are sure that one moment has passed, one second, say, has passed. How fast this clock undergoes this transition is the thing that defines the precision of the clock. The faster it orthogonalizes, the more precise, the more thinly we can slice the timeline, and the more precise we have a clock we have. The parameter that measures this precision, or more the opposite of this precision, this uncertainty, is called the orthogonalization time, which is here defined, is inversely proportional to the energy. What this means is that if we want to have a very precise clock to measure, say, time here, I would have to invest a lot of energy here. And this is a very well-known result. It comes from purely quantum mechanical reasoning, purely quantum mechanical considerations. Now I would like to sketch a bit of an idea what would happen if we put gravitational effects if we take them into account. So we know by the mass energy equivalence that having some energy, somehow energy density localized, stems a gravitational field. So if the energy is E0, this clock would be time dilated by some rate corresponding to this mass, let's say. If this energy is E1, this clock would tick slower than if the energy would be E0, because this energy is greater, right? And then it causes a greater time dilation. But the point is that because the system is a clock, it's neither in E0 or in E1, it's in a coherent superposition of E0 and E1. So what happens is that by the mere fact that this system here is a clock, this other clock does not know how to tick. It does not know whether to tick time dilated with respect to E0 or E1. And the uncertainty for time dilation of this clock will be proportional to the energy difference. So we have some sort of Heisenberg uncertainty relation about the precision with which we can measure time here and the precision with which we can measure time here. Or in other words, we made a simple model in this paper of this situation in which the clocks interact via a Newtonian potential, but where the mass is substituted by an operator, and the clock can have different values of this energy. And what happens is, of course, that the clocks get entangled. So what I said is simply, when the clock is at 0, this one ticks at a normal rate. When the clock is at 1, the other clock ticks slower, so the clocks get entangled. And then if we are interested, let's say, in measuring time in this clock, because it gets entangled, when we forget about the other clock, trace it out, we find a mixed state, and we find that there is a limitation for how well we can define time at this point due to the gravitational interaction between the clocks. So this is a result of a paper a long time ago, and we were interested to find that there was this limitation, but nevertheless in the analysis there was something that we didn't find quite compelling, because the whole philosophy of the work was to say what we mean by time is whatever is measured by a clock. But nevertheless, whenever you want to solve the system and analyze the quantum mechanics of the system, you have to evolve things with the Schrödinger equation with respect to some parameter time t. And this time t, where does it come from? Who tells us what is this? Can I understand it as what is measured by a clock, or is this something kind of given from the outside? And this is even more profound in view of the fact that we claim that the structure, that the metric of space-time is not classical in these situations, because the clock is in a superposition of energies. So if we would have a classical metric, then this time would be very naturally given by this. But in this situation, it is not. So how can we define it? How can we understand it? And can we give an operational meaning to it? This was the reasoning, or following the philosophy of defining time operationally. Can we also, this time that we use to as a parameter in the Schrödinger equation, define it with respect to a clock? And then this comes then the second part of my talk, which is using quantum clocks as quantum reference frames to define this parameter time. So the way we analyze this problem in order not to, let's say, contradict our own philosophy of time is that what is measured by a clock, was to use this Page-Wouters formulation of quantum mechanics or dynamics. This Page-Wouters formulation of quantum mechanics or dynamics is a way to recover the normal, say, dynamical description in some specific situations of quantum mechanics from a state that is not a state that fulfills the Schrödinger equation, but rather a state that fulfills a constraint equation. This is very much motivated, of course, by general relativity. That is a theory with constraints. So if one has a Hamiltonian for the clock and a Hamiltonian for the system, and one requires that the full system is annihilated by this Hamiltonian, it turns out that by conditioning on the clock measuring a certain time t, the state of the reduced system pertaining to this part, to the system itself, is something that fulfills the Schrödinger equation. So it's a way to describe dynamics not from a state that evolves in time in some parameter that is somehow God-given, but rather something that some parameter that is given by the eigenvalues of some operator, right? So it's something more operational, like really what the clock measures, and I define time evolution by the correlation between what the clock measures and how I see the system when the clock is measured. So one reproduces perfectly the Schrödinger equation when the clock is perfect, or in other words, when the clock is perfectly distinguishable with respect to time translations, or in other words, when it carries the regular representation of the group of time translations, okay? So this is, of course, very well studied. This is not new. This has been proposed a long time ago, and it's deeply related to works in quantum gravity that study this problem of how to define observables, how to define time evolution for constrained systems, in particular general relativity, right? So this is nothing new. What we are using it for, or what we did, was to say, what happens if we don't have only one clock? What happens if you have more than one clock, so that you can have several reference frames to describe dynamics? What we did was building a framework that, given the dynamics and the description of states with respect to a given temporal reference frame, allows us to find the dynamics and the states with respect to another reference frame, and then compare the two. And then say, evolution is unitary with respect to this one. What can I say about the evolution with respect to this one? Or this event is localized in time with respect to this frame. What can I say about the event with respect to this other frame? And so on. So these are the kind of questions that we started to investigate, and in particular in cases where you have a superposition of masses, for example, or of energies, where the background of space-time is not well defined. So this is the type of picture that we had in mind. So in particular, for the problem of the clock's interaction gravitationally, we consider that situation with three clocks, A, B, and C. C is far away from A and B, so that its gravitational interaction can be neglected. It's like kind of far away from everything. And of course, if one conditions on time having a certain value with respect to clock C, one recovers, this is trivial, one recovers the usual time evolution that we had before for the external time. But this is not the only thing that you can do. You can also condition on clock A, for example, and look at what happens to the evolution of clocks B and C. And when you do that, you can compare these different descriptions of the dynamics with respect to different clocks. So it's kind of easy to see, basically because of the fact that all these operators commute, that if one conditions on clock C, on clock A, one finds a unitary evolution of clocks B and C. So this is perhaps a bit surprising in view of the fact that I told you that clocks A and B get entangled, right? So in principle, one would say, oh, they get entangled, so the evolution with respect to one of these clocks that gets entangled is necessarily mixed. But then when you do this analysis a la Page-Wouters, you find that the evolution with respect to clock A is not, let's say, some sort of Lindblad equation or something like that. Is actually what you have is a unitary. Why is this the case? Or why this is, so what's the key aspect that we are maybe missing to jump into conclusions to say evolution has to be, I don't know, dispersive or noisy? And the key observation is that we are describing different systems with respect to different reference frames. So it's true that A and B get entangled. It's true that it's true that the reduced state of A is mixed after some time of interaction between A and B. But this is a statement that is made from the reference frame of C. When I make the statement from the reference frame of A, it does not necessarily mean that A will see things decohere. In fact, entanglement and superposition are reference frame dependent things. So this is kind of one of the results of first of our work. And maybe an analogy is useful to understand this. So consider some external observer, let's say Eve for external. And Eve describes the blue particle and the red particle. And she prepares these two particles in this state, 0, delta, 1 minus delta, 1. So this is an entangled state for Eve. And then we can naively ask the question, how would the blue particle see the rest of the world, in particular the red particle? And we can say, oh, because it's entangled, it will see everything else kind of decohered. But this is not the case. So this is a very particular state, a very special state. If we look closely, every time in each amplitude of this superposition that makes the state entangled, the relative distance between the red and the blue is delta. And then, using the formalism proposed in this paper here, so I want to say this is not some, I'm not appealing to intuition here, only there's like a rule, a formalism that tells you how to jump to the reference frame of the blue particle. And then if you use it, you indeed find that the blue particle sees the red particle not in a mixed state, but rather in a pure state localized at delta, as our intuition would tell us. So what we're seeing here is that this superposition, whether a state is in a superposition, entangled, etc., depends on the reference frame who is looking. So what I think it's at the core of this phenomenon, or at the core of this feature, is that the notion of subsystem changes. And obviously, if you define a subsystem, this goes together with defining what is entangled and what is not. And I will talk about this later. Now, let me talk about events. So I talked about entanglement. This was not extremely operational because I didn't talk about measurements. I didn't say what happens if you measure some system here and there, and how would you describe these measurements with respect to clock A and clock B and so on. So in order to do that, first I have to introduce how to deal with measurements, or at least a way to deal with measurements in this Page-Wouters. So this Page-Wouters is some sort of block universe description of physics. So everything that happens is described there, and if you want a time slice reconstruction of the things that happen, you just condition of one of the clocks. So in particular for measurements, a way to describe them, is to put them into the Hamiltonian, to purify them, and to say I have a system, I have an ancilla that records some information about the system, and I'm going to condition this interaction when by the clock measuring a certain time. So what this tells us is that when Alice's clock shows time TA star, then the operation Ka, which is an operation that acts on the joint system of the ancilla and the system of interest, entangles them in general so that we can measure, this operation is applied. So when I treat this not at the, say, Hamiltonian level, but at the evolution operator level, this Ka is something like the logarithm of a Krauss operator, or something like that. Okay. So we do the same for B, and we apply this logic, but now to the more complicated situation in which we have a background that is perhaps not classically defined due to the fact that we have a mass in a superposition, for example. And this is what we did. So this is perhaps the cleanest example of one of these situations in which gravitating quantum system leads to an indefinite causal structure. So this indefinite causal structure is a situation in which the order of events is indefinite. In one branch, A happens before B, in another branch, B happens before A, and so on. And it turns out that with gravity, you can get such a situation. This is very nicely proposed in this paper here. So the situation is as follows. Consider Jupiter, a very massive object, and consider Alice and Bob. Alice and Bob have clocks, and they condition their measurements on some systems depending on what the clock read. So they say, whenever my clock shows 12 o'clock, I will trigger an interaction between a system and an ancilla, or I will trigger some measurement, some event on the system. And both of them do it for the same time, but with respect to their own clocks. So there's two operations, Alice and Bob, and for Alice and Bob, these operations lead to some events that one can question whether one happens before the other and so on, whether one can influence the other. So this situation has been described in several ways. In particular, one of them is this language of process matrices or quantum comps, etc. What we did was to somehow build a connection between quantum reference frames and indefinite causality by explaining this situation with a Hamiltonian killing an overall kind of block universe quantum state. So the Hamiltonian is this one, and it basically includes three clocks again. So this index I goes for A, B, and C. We include the gravitational interaction due to Jupiter, but crucially, we let this gravitational interaction be governed by a quantum operator. So I want to say that Jupiter can be to the left of Alice, in which case Alice's clock runs slower than Bob, in which case her operation goes before Bob's operation, or it can also be to the right. And in this case, the opposite happens. Then Bob comes later than Alice. But importantly, it can also be in a superposition between being here and here, like this. And if it is in a superposition, the way to describe it is just to let this gravitational potential depend on the quantum operators. And these quantum operators in this case are the relative distances between Jupiter and Bob and the relative distance between Jupiter and Alice. You do this, you postulate that the state has to be annihilated by this constraint. This is, of course, a very toy model of something that would happen more complicatedly in general relativity. When you do that, you find the history state, or you find the state, the block universe state that describes all the events when the clock is measuring certain times. And what you find is effectively what you expected to find, that there is a superposition of causal order. In some branch, when the mass is on the left, it is B, the one who acts before A. When the mass is on the right, it is A, the one who acts before B on the system. And what we're interested in now is to kind of doing a map of space-time and try to localize events as measured by the different clocks. So this is the description of the C guy, the one that is far away from all of them, who sees a very symmetric situation. In one branch, Alice acts before Bob, and in the other, the opposite happens. And then, if we would like to geometrically depict where the events are, a way to do it is, because you don't have a single space-time in some sense, because you have a superposition of masses, you would need, in some sense, two manifolds. And this is, or not in some sense, but you can depict it if you have two manifolds. So this is a bit of a different picture of an event. An event usually geometrically is a point on a manifold. The description that I want to give is an identification of points in two manifolds. So you have the manifold where the mass is on the right, the manifold where the mass is on the left. And then for Charlie, for the guy far away, it comes for the manifold where the mass is on the right, Alice's event happens at time t minus delta. And for the mass on the left, it happens at t plus delta. And the opposite happens for the case of Bob, so that we have indefinite causal structure. In this case, the events, I call them events because there's like an operationally meaningful statement of something happening to a quantum system. But it's not a point on a manifold, and it's not, if you look at a single manifold, these are not things that are localized in time, because this event has a quantum uncertainty. Sometimes for some amplitude, with some amplitude it happens at t minus delta, with some other amplitude it happens at t plus delta. What we did is we said, okay, this is the description from Charlie, can we find a description from Alice? And if you do the description from Alice, you find the following graph. So you find, again, a state that in some sense factorizes out for Alice's operation, because Alice's operation is always the same, applied at the time t star. And this is depicted here in the two manifolds. If you take the two manifolds, you see that in the manifold on the right, in Alice's description, the time happens always at t star. In the manifold on the left, in the description of Alice, the event happens also at t star, not at t minus delta and t plus delta. With respect to her, the event is perfectly localized in time. Bob is not. Bob's is not. Bob's is also diffused in time. So you can maybe argue that an indefinite causal structure is a structure in which you cannot have all events localized in time with respect to all clocks, maybe. Okay, so the main result of this part is to say, with gravitating quantum systems, we have to think of a more general notion of events, geometrically, not necessarily like some point on a manifold, but events can be localized or delocalized in time with respect to different clocks. We can find clocks with respect to which certain events are localized. And this can be useful, of course, because if we're interested in a particular event, it's way easier to analyze it if it's localized with respect to this clock. So now I would like to talk about, this was a very kind of intuitive description, the one I gave. Now I will go a bit more maybe mathematical, but I think it's nevertheless a description that that points to the right issue that is behind these different relativities. I'm not so sure about whether it's precisely the thing that gives us the relative localization, but the relativity of entanglement in space, I think this is for sure. So the picture I have in mind is the following. There's Alice. She has a reference frame for a certain group. So we have a certain symmetry. Alice has a reference frame for that symmetry. And there is a system. And she measures that system. And when we say that she measures that system, she measures the relative degrees of freedom between her system and her reference frame. So we want to say that Alice has a perfect reference frame. What this means is that she's able to prepare states that correspond to group elements, and these states should be orthogonal to each other. So for example, if we talk about translations, the reference frame is a very localized particle. And then if I move a little bit this very localized particle, I can perfectly distinguish the very localized particle before I moved it and after I moved it. So mathematically, this means that the Hilbert space of the reference frame carries the regular representation of the group. And this has important consequences that I will not go into details, but let's say it's like that. And on the other hand, the system is general. The system can carry the regular representation as well. It can be another reference frame, but it carries some unitary representation. And then the key observation here, or this will be like a more kind of algebraic treatment of reference frames and how to switch between them. Sorry, how am I doing in time? Or 10 minutes. I have 10 minutes. Okay. So the key observation is the following. So imagine Alice measures something in the system, and she says, measures or interacts in some way. She says, more generally, I apply operator O on the system. How would this be translated from the point of view of some external guy that sees everything happening and that perhaps has control over all degrees of freedom, including the reference frame of Alice? So Alice has no external reference frame. All she has to measure or with respect to which she can tell translations, rotations, etc., is this surfboard, is this regular representation for her group. But there is some external guy that is more powerful and can distinguish both systems. So when she says, I apply operation O on the system, the external guy actually sees her applying this operator, which is a quantum controlled operation controlled by the state of her reference frame. For example, if she were to measure position, and she says, I'm measuring the position of the particle, what the external guy would see is actually, not surprisingly, she's measuring the relative position between her reference frame and the system. And so if you plug in here x, you would get x minus x surfboard. So these are invariant operators. These are operators that do not depend on any external reference frame, in the sense that if I rotate everything, they don't change. If I translate everything, they don't change, and so on. They're invariant under the, say, global action of the group, whatever the group is in question. And in this sense, they're independent of an external reference frame, and in this sense are all the degrees of freedom that are available to Alice. Not to the external guy. The external guy is possibly more powerful, but Alice has only access to these relevant degrees of. If I'm here inside this room, I cannot measure the, say, velocity of this room, but I can measure the relative velocity between things that are inside the room. Okay. So what's the Hilbert space description of these operators? For the external guy, this Hilbert space description, these operators are non-trivial both in the what the external guy assigns to be the reference frame of the surfboard and what the external guy assigns to be the reference frame of the atom, right? So they have, they're non-trivial in both of them. But nevertheless, these things form an algebra. These operators relative to A form an algebra, in the sense that if you multiply two of them, you get something that is also of that form. And since it's an algebra, one can repartition the Hilbert space in such a way that this corresponds to a given tensor factor of the Hilbert space. So if we want to jump now to a preferred factorization that we want to call the reference frame of Alice, we need to refactorize the Hilbert space from the description of the external guy to the description of Alice. It's important to note that the external guy is more powerful, so we would have to take into account the fact that Alice does not have necessarily access to all the degrees of freedom, only those that are invariant. But there is such a unitary, let's say, called U dagger of G hat, defined in this way. And if you apply this to operators of the form A system relative to Alice that I defined before, you get that they factorize in a specific tensor factor of the Hilbert space. So I think this is at the core of the relativity of entanglement and superposition. Alice and Bob are not measuring the same degrees of freedom. Alice is measuring the system relative to her frame. Bob is measuring the system relative to his frame. And there is a way to translate between each other. And it's possible that when measuring these observables, the state is factorized with respect to one partition, but not factorized with respect to another partition. So this is just, there's many more things about how this Hilbert space decomposes, but I think I will not go into this. The important thing is that there's a refactorization of the Hilbert space, and that there is one for Alice, and obviously there is also one for Bob. If Bob carries a regular representation of the group, this is also the case. And what we did in this work, basically the main result of this work, is we found ways to translate from one to the other, or to translate one tensor factorization to the other. So what the trick to do it is this, following this perspective neutral logic of this paper here, which you can relate both of them unitarily to the external guy, then both of them are unitarily related to each other, of course. And so this is the main message. Like, this picture is maybe the main message of this part of the talk, which is there is the invariant subsystem, all the degrees of freedom that are accessible only to internal observers. And there's two different partitions if you have two different observers or two different regular representations and so on. One is that with respect to Bob, which partitions the invariant subsystem in this way with this kind of horizontal threads. So in this diagram, whenever these blocks represent algebras, and whenever two algebras overlap, it means they don't commute. Okay, so if you look at this one, for example, the system relative to Alice and the system relative to Bob, they don't commute, they overlap, but they're not the same. And this is the important thing. And if you would like to translate from one to the other, you have to consider the full description of the algebraic description of the full kind of invariant system in order to find such equations. And what we found was that these equations actually reduced to the equations that were found before in the original quantum reference frame transformations paper. So I think this is kind of at the core of this phenomenon. So thank you.
Thank you, Esteban, for the talk. Do we have any questions from the floor or from online? Nothing online. Anything from the floor? Borivoyo?
Thank you, Esteban. Perhaps like more conceptual question, I need kind of clarification from the beginning of your slide when you discussed three parties, A, B, and C, and then you said, well, it's true that A, B get entangled. That means reduced state of A is, let's say, mixed state and so on. So you see the coherence, but this is only from the perspective of C. If you jump in the reference frame of A, it's still unitary. But then the same reasoning applies to C, right? Because there could be a D such that somehow you say, well, C should see also unitary dynamics, so to speak. How then we see the coherence? This is the, you understand what I mean or not really?
Yes, I think...
so I can always purify, I can always say, oh, well, there is like, again, some external system, and then somehow there is no kind of conceptual way, fundamental way to see.
For D, there will be like a unitary evolution of the, say, A, B, and C system, right?
And then you jump on C and say C should see unitary, not the coherence.
Okay, so C is a unitary evolution for A and B. The evolution of the A and B system is driven by a unitary, but A and B get entangled by this unitary. And then when you trace out one, the state becomes mixed. And then one can naively think that this fact implies that the evolution with respect to A becomes decoherent, but it's not. But it's not a statement about. So I was trying to maybe a bit naively argue that a statement about the state would lead to a statement about the evolution with respect to the guy that I jumped to. But this is not the case. But one could think in principle that this could be true. But what we show is that it's not true. The state becomes mixed, and therefore one might think that the evolution with respect to that thing for which the state becomes mixed is decoherent, but it's not.
Thank you. Yes. Okay.
Any other question? Yes, there is a question there.
Hi, thanks for the nice talk. I'm a bit confused by the notion of superimposing manifolds, because a manifold is mathematically a very formless object. It just tells you the topology, what is next to what, and you can equip the same manifold with different metrics, hence different causal structures. So I'm not sure I agree that when having like superpositions of masses, we should think of that in terms of superpositions of manifolds. I would say rather we should think in terms of observables and that live on the same manifold but can then be in superposition. But perhaps this is kind of a...
Yeah, I mean, there is no... at this level, this was just a picture to highlight the point that what is local with respect to one observer is not local with respect to another one, and that you can depict it in this way. But there is no formal mathematical definition of what I mean by this superposition of manifolds. maybe one can develop one, but I think Lucian Hardy has done some work towards that. But it's like taking unions of manifolds and also identifying points between the manifolds and letting the maps that identify these points to change in a way that you don't allow only coordinate transformations that stay within one manifold, but you allow coordinate transformation that also change the identification of the points. But so as far as my talk is concerned, this is just a picture. Yeah, I don't know. It would be interesting to develop this kind of notion. I'm not sure if one can rigorously mathematically. But what goes on here is basically that. Like if you see here in the left manifold, there is a transformation that moves this point downwards, but on the right manifold is not that transformation. We move the point upwards. So we're applying kind of a coordinate change that is different for different manifolds. And this is what allows us to say, or to depict this fact that localization of points is relative. But I agree with, yeah.
There's a question from Rainer.
So some of this looked extremely familiar for me from the point of view of constructing covariant POVMs. And so maybe you have a comment right away, but beyond that, I would like to have a chat with you to sort these things out. Like, how is that actually different or the same?
Okay.
So, yeah.
Yes, there is. This equation is very is how you do it. Yeah. So this is we didn't develop this equation. Of course, this is something that we adopt as kind of an input, and then what we do is we take this equation and use it to refactorize the Hilbert space and say, okay, this is Alice's description, and it turns out that it matches exactly the previous kind of quantum reference frame transformations. I think so. I would say so for safety, but yes. The twirling, yeah. No, I think for being absolutely mathematically rigorous, I think to be on the safe side, I would say it's compact. Yeah, but but maybe one can also say something about non-compact. Like if one applies this to the translation group, for example, one finds physically meaningful thing, although of course infinities. But one can, yeah.
Is this a question?
Yeah, it's just to Wolfgang's remark. As far as I understood you, this could be two topologically identical manifolds. So it depends on how you define. I guess, as you said, form laws is just topologically is identical, but just the order of events or at most metric could be said that is different than on the same manifold. I guess this.
Okay, I had a very silly question. When you showed your the Hamiltonian that where the entangles the clocks, right? And then the one clock goes faster than the other.
This one?
Yeah, before the previous some previous slides. Here. Well, I would have expected this equation to be symmetric in exchanging Alice and Bob, but there is the 0-1 term has a phase that the 1-0 term does not have. So
yes, it depends how you define the origin of the energy. Like here, this equation here is defined with the origin of the energy such that E0 equals 0.
For both. For both.
Yes, for both. Yes.
Then again, why the term 1-0 does not have that phase? The initial state had already something that compensated for it. Okay, fine. Okay, I guess there's another question. I think we are very grateful to the speaker for taking less time than expected, so we are back on time. So we thank Esteban again.